Hey there! Welcome back to the Noctis on YouTube. Boeing, one of the most iconic American companies, stands alongside renowned global brands such as Coca-Cola, Amazon, and Apple. Although its components come from various places around the world, all of Boeing's final assembly lines are based in the US, with an additional finishing and delivery center for the 737 in China. Let's explore this production process more deeply, from the origin of the parts to the final assembly. Creating an airplane is an extraordinarily complex process. The Boeing 737NG, for example, consists of about 500,000 parts, while the Boeing 777 is made of about 3 million different parts. Of course, not all parts are made at the same place or by the same supplier. Each supplier provides its own specialization and expertise. For example, the wingtips for the Dreamliner are made in Busan, South Korea, while the landing gear is produced in Gloucester, England, and its horizontal stabilizers in Foggia, Italy. In the US, some of Boeing's main contractors include Spirit Aerosystems in Wichita, Kansas, Honeywell in Charlotte, North Carolina, and Triumph Group in Berwyn, Pennsylvania. On the other hand, the main engine suppliers based in the US are General Electric and Pratt & Whitney, while Rolls-Royce is headquartered in the UK. Boeing's main production facilities are located at 3 different sites in the US: Everett and Renton in Washington State, and Charleston in South Carolina. The facility in Everett, first opened on May 1, 1967, was specially built to produce the 747 jumbo jet. The team working on the first 747-100 faced various challenges as they completed the aircraft while the factory was still under construction. Due to their hard work, they earned a nickname of honor, the Incredibles. The main factory in Everett currently occupies a space of 472 million cubic feet, which spreads over an area of 98.3 hectares, making it the largest building in the world by volume. The factory is equipped with 6 large doors on the south side, which can be opened with just a press of a button, and takes about 5 minutes to fully open. The facility accommodates around 36,000 workers every day, equipped with various amenities such as a fire department, bank, childcare centre, a fully equipped medical clinic, and water treatment facilities. However, one thing that is absent in the Everett factory is an air conditioning system. The temperature is regulated by opening the large doors and using fans or turning on more ceiling lights to warm the air inside. The original factory was expanded in 1978 to accommodate the production of the Boeing 767, and once again in 1992 for the Boeing 777 program. Recently, additional structures have been added to handle the robotic assembly for the 777 fuselage and the fabrication of the composite wings for the 777X. Boeing 777X wing testing process. Boeing implements a meticulous testing process to inspect the wing spars, the structural backbone of the 777X aircraft, using NDI non-destructive inspection robots. This advanced technology allows the detection of unseen defects, such as foreign materials and air pockets, to ensure the reliability of the wings. ProTag NSR project. In this project run by the Center for Lightweight Production in Augsburg, the main focus is to push the boundaries of automation in the manufacturing of large-sized aircraft structural components. This involves various processes, from preforming structural layers to the automatic application of stringers and vacuum packing. In the manufacturing of these large components, a series of technologies and automation techniques are applied, including the use of rolling effectors, reinforcing patch performing, and modular gripping systems to detect and move the cut pieces. The system also integrates optical sensors and fiber angle cameras to monitor and ensure quality during the draping process. Every step of this manufacturing process is meticulously designed to ensure the quality and strength of the structural components. This includes thorough inspection of each applied piece and the use of robots with customized end effectors to match the target geometry of the tool. Gripper module and draping process. The gripper, equipped with 127 suction modules, operates automatically to move the cut pieces to the tool, layering these reinforcing pieces. The modules within the gripper play a crucial role in altering the pieces to fit the target geometry during the transfer. These modules adjust the pieces to achieve the desired draping on the tool surface. Optical sensors within the modules monitor and ensure the quality of the draping process. Quality assurance and robotic integration. To guarantee the precision of each applied piece, a deep quality inspection is performed. Fiber angle cameras are used to inspect the draping quality, while laser sensors with external positioning verify the accurate edge detection of the pieces. For the application of long structural layers, collaborative robots are used. The end effectors of these robots are carefully adjusted to match the target geometry of the tools. An algorithm calculates the collision-free movements of both robots, ensuring synchronized and precise placement. Module adjustment and stringer application. The process of adjusting modules for collaborative robots involves several steps. First, the current position of the modules is measured. Then, the target configuration of the modules is set, allowing for accurate pre-draping of long pieces. In automatic stringer application, stringers critical for reinforcing the structure are automatically picked up by specially developed multi-kinematic grippers. These stringers are then precisely positioned on the preform, contributing to the structural integrity of the component. Fixation and vacuum packaging. The automatic fixation of vacuum packaging involves the application of epoxy resin to fix additional material packages based on a computer model that acts as a digital twin. This allows for precise and controlled resin application. The robotic measurement cell is configured for safety, and the robot paths are programmed and simulated offline to prevent any collisions. Semi-automatic outer vacuum packaging facilitates the vacuum infusion process, where a semi-permeable membrane is positioned within the tool and sealed. A mechanical system, operated by multi-kinematic grippers, consistently and pressure-controlled compacts the membrane, preparing the stage for the infusion process. Final step: quality control and curing. The final step involves infusing the preform with RTM, resin transfer molding epoxy resin. The cured resin produces a composite part that is strong and structurally sound. Aerosystems, a pioneer in aerospace manufacturing. Aerosystems stands as a prominent name in the aerospace manufacturing industry, recognized globally for its intricate contributions to the production of aerodynamic structures for various types of aircraft. With a global presence encompassing facilities in the United States, the UK, France, Malaysia, and Morocco, the company stands as a vital player in the aviation supply chain. Headquartered in Wichita, Kansas, the company has established itself as the largest first-tier producer of aerodynamic structures in the world. At the core of its operations lies the complex task of creating aerodynamic structures for commercial aircraft, defense platforms, and business regional jets. These components include aircraft fuselages, integrated wings, wing components, pylons and nacelles, each playing a critical role in structural integrity, aerodynamics, and the overall performance of modern aircraft. Spirit's manufacturing capabilities encompass an impressive range of products, with its contributions covering a wide spectrum of aircraft models. A notable achievement for the company is its involvement in the production of the Boeing 737, a popular narrow-bodied aircraft that revolutionized commercial aviation. With a rich history spanning over 50 years, the Boeing 737 has evolved in design and technology, and the company has been a primary driver of this advancement. The company's dedication to excellence extends its contributions to other Boeing aircraft models, including a significant role in the manufacturing process of the Boeing 787 Dreamliner. Spirit Aerosystems plays a pivotal role in the production of Boeing's revolutionary 787 Dreamliner. With its main facility in Wichita, Kansas, Spirit is responsible for creating critical components that contribute to the Dreamliner's advanced design and performance. Notably, the company has achieved a remarkable milestone by successfully delivering crucial elements for the 500th Boeing 787 Dreamliner. Advanced manufacturing in Wichita. At the heart of Spirit's contribution lies its facility in Wichita, where it undertakes the fabrication of the Dreamliner's front fuselage and engine pylons. These components are critical for the aircraft's structural integrity and overall aerodynamics. Furthermore, Spirit's facilities in Tulsa, Oklahoma, and Subang, Malaysia are central hubs for producing stationary wing leading edges and movable wing leading edges, which are vital for the aircraft's aerodynamic efficiency. Innovative assembly process. One remarkable achievement of Spirit is its ability to provide Boeing with a fully integrated front fuselage structure. This section, known as Section 41, is a composite masterpiece built using state-of-the-art automatic fiber placement machines. These machines intricately form composite tapes to create a single fuselage section, showcasing Spirit's advanced manufacturing capability. This assembly process is optimized through Spirit Exact, the company's exclusive methodology that utilizes pre-positioned holes and an automatic rivet mounting system. This innovation enhances efficiency and precision during assembly. Aerosystems' collaboration with Boeing has been a pivotal point in revolutionizing the aviation industry. The Dreamliner program introduced groundbreaking advancements by pioneering the large-scale use of composites in commercial aircraft, resulting in improved fuel efficiency and reduced operational costs. This transformative approach underscores the aviation industry's commitment to sustainability and technological progression. Transition to a dynamic assembly line. Since its inception in 1966, the manufacturing process of the Boeing 737 MAX has undergone remarkable transformations. The most significant change is the transition from traditional static assembly methods to a dynamic moving assembly line, a technique reminiscent of automobile production. This innovation not only accelerates manufacturing, but also reduces production costs and minimizes order delays. Implementation of the moving assembly line. The concept of the moving assembly line, initially devised by Henry Ford, has been adeptly adapted to aircraft manufacturing by Boeing. Unlike traditional methods where the aircraft is built in a stationary position, the 737 MAX moves along the assembly line at a rate of 2 inches per minute. It only stops for essential breaks, critical production issues, or between shifts. Marked timelines on the floor provide workers with a visual reference of manufacturing progress. Production sequence and final assembly. The production sequence begins with the arrival of the fuselage in Renton. Wires, pneumatic and cooling ducts, and insulation are integrated into the fuselage before it is lifted onto the moving assembly line. Subsequently, the tail fin is lifted into position by an overhead crane and securely attached. The aircraft undergoes several tests, including cabin pressurization tests and landing gear system checks. The cabin interior, including seats, restrooms, baggage bins, and ceiling panels, is then finalized. The final stage involves engine installation. Material composition of the 737 MAX. Boeing utilizes various aluminum alloys, as well as fiberglass materials, Kevlar and graphite epoxy in building the 737 MAX. Different alloys are used for different components based on the desired properties, such as strength and resistance to corrosion. Construction and customization. Once construction is completed, the aircraft undergoes a test flight before being transported to Boeing Field in Seattle, where it is painted and customized according to customer specifications. About 200 liters of paint, weighing over 130 kilograms, are used per aircraft. Efficient production and goals. The Boeing 737 MAX consists of about 600,000 parts in total. Over time, Boeing has streamlined the production process, reducing the manufacturing time from 11 days to a targeted 8 days. The 737 MAX production rate has substantially grown over the years. In 2005, Boeing produced 31 aircraft per month, which increased to 42 per month in 2014, indicating Boeing's commitment to enhancing efficiency and meeting growing demands.